We are discussing the problem of distributed deadlock detection, and in the last class we just started with an example that suppose we have in the distributed system three machines, and we name the machines as M0, M1, and machine M2. Then suppose in machine M0 we have three processes. So one is process 0, process 1, and process 2. Here again we have three processes, 3, 4, and 5, and we assume that here there are four processes, process 6, 7, 8, and 9. Okay. So the problem that we took was something like this. Suppose process 0 puts a request for a resource which is currently held by process 1. Process 1 puts a request for a resource which is currently held by process 2. So effectively what we are doing is we are removing the resource nodes in this resource allocation graph. So we are converting this to an wait for graph. So as if process 0 is waiting for some resource to be released by process 1. Okay. Similarly, process 2 of machine M0, that is waiting for some resource to be released by process 3 of machine M1. This process 3 in turn is waiting for two processes, process 4 and process 5, and both these processes are in machine M1. Process 4 is waiting for a resource which is currently held by process 6. Process 5 is waiting for a resource which is currently held by process 7. Process 7 is waiting for a resource which is currently held by process 9. Process 6 is waiting for a resource which is currently held by process 8. Okay, and process 8 is waiting for a resource which is currently held by process 0. So this completes the cycle, this path 0, 1, 2, 3, 4, 6, 8, then back to 0. So this part completes the cycle in the graph, and so these are the processes which are likely to be in deadlock. Okay. Now, as against in our centralized deadlock detection, where we have assumed that we have a central coordinator which is nothing but a particular machine which is connected in the network, which is responsible for detection of deadlock by looking at the global distribution graph. In this case, we assume that all the machines, they take part in the deadlock detection process. Now, how that can be done? Whenever any particular process puts request for a resource, either the resource will be immediately granted if the resource is not currently allocated to some other process, or if the resource is currently allocated to some other process, then the process which has requested for the resource, that will be blocked because it does not get the resource. Okay. So if we assume in this graph that say at particular instant of time it is process 0 which has put a request for resource for some resource, the resource is allocated to process 1. That means process 0 is blocked. So whenever a process is blocked, that particular process generates a message. Okay. The message consists of three components. It will consist of the process number of the process which is being blocked. Okay. Then it will generate the number, say another number process Pj, which is generating the message. Okay. And it will generate another process number Pk to which the message is to be sent. Okay. So what is this Pi? All these three are process numbers. Pi is the process number which is currently blocked, which is just blocked. Pj is the process which is generating the message, and Pk is the process identification number to which the message is being sent. Okay. So in this particular example, when we are assuming that it is process 0 which is just being blocked. So process 0 will also generate some such message, and in this case process 0 will generate a message. So it is process P0 that is generating a message having three components like this, and the components in this case will be firstly the process identification number which is just blocked, so that is 0 because it is the 0th process that is being blocked. Now in this case this is the process which is generating the message, so the second component will also be 0, and the third component is the process identification number to which the message is to be sent. So in this case that is process number 1. Okay. So this is a message which is generated, a special message which is generated by process P0, and the message is sent to process 1. Okay. Process 1, on getting this message, it will modify this message and it will generate a modified message. In the modified message, the first field will remain unchanged because this indicates the process which has just been blocked, but process 1 is not just blocked. So process 1 will retain the first component of the message. Now the second component becomes the identification number of process 1 itself because it is generating the modified message, and the third component is the identification number of the process to which this modified message is to be sent. Okay. So on receiving this message from process P0, process P1 will generate the modified message. The modified message will be 0, 1, and 2. Okay. So if you continue this way, you find that when you come to this link, when process P2 generates the message, P2 will get this message. It will replace the second component in the message by its own identification number, and the third component by the destination to which the process P2 will send the message. So here the message will be 0, 2, 3. Okay. 3 similarly will now generate 2 messages because 3 is waiting for 2 processes. Okay. So here on this link 3 will send a message 0, 3, 4, and on this link it will send the message 0, 3, and 5. Okay. This process 5 will send a message to process 7 having components 0, 5, 7. Process 7 will send a message to process 9 having components 0, 7, 9. And after that this message cannot go anywhere because process 9 is not waiting for any other process. In this path, process 4, after getting this message, it will modify this message, and the modified message will be 0, 4, 6. And this message is sent to process 6. Process 6 will modify this message, and the modified message will become 0, 6, 8. And this message is sent to 8. Process 8, which is waiting for process 0, will send the message, will modify this message, and the modified message will be 0, 8, 0. Okay. Now when process 0 receives this message, it finds that the originator of the message, that means the process which has just been blocked, and the destination to which the message is coming, they are identical. Okay. Because you are getting the message back to the same process, that indicates that there is a cycle, and because there is a cycle, there is a deadlock. Okay. Whereas in this path, this message does not come back to process 0 because 9 is not sending this message to any other process. Okay. So this path does not lead to deadlock, whereas this cycle leads to deadlock. Okay. So every process, after sending the message and when it gets back the message, it finds that the originator process number and the destination process number, if these two are identical, that indicates there is a deadlock. And you find that in this case, every machine or every process has taken part in the determination of deadlock. Okay. So once the deadlock is detected, the next job is to come out of the deadlock. The deadlock has to be broken. So one option that can be given is, when process 0 gets this message, it finds that the request put by process 0 has led to the deadlock. So the process 0 may commit suicide. You ask process 0 to be killed, and that will break the deadlock. That is the simplest solution. But that has a disadvantage. You consider a situation like this, that in the same cycle, suppose two processes are blocked simultaneously, because all of them are independent processes and they are running on different machines. So it is quite possible that more than one process can be blocked simultaneously. Okay. If it is like this, that process 0 is blocked, at the same time process 6 is also blocked. Okay. In that case, process 0 will generate this message 001, assuming our path remains the same. Process P0 will generate the message 001 and the message will be sent to process 1. Process 6 will generate another message and the message components will be 6, 6, 8. Because process 6 is also blocked and this is an independent process, it will generate another message having the process identification number which is just block, the process identification number which is generating the message, and the identification of the process to which the message is to be sent. So process 6 generates a message having these three components. So simultaneously, this message and this message, both of them are circulated through this cycle. Okay. So ultimately, process 0 will get back this message when process 0 finds that the request put by process 0 has started the deadlock. Process P6 will finally get a message of this form: 6, 4, 6. And this message will be generated by process P4 on receiving modified version of this message, and the message will come to process 6. Okay. So in this case, you find that both P0 and P6, they find that both of them are responsible for the occurrence of deadlock. Okay. So both of them will commit suicide. Whereas killing only one process is sufficient to break the deadlock. So you can have a situation that you can kill more than one process simultaneously to break the deadlock, which is not necessary. Okay. However, the deadlock will be broken. Only thing is, more number of processes may be killed. So to avoid this problem, what can be done is that whenever a message passes from one process to another process, every process attaches its own identification number to that particular message. Okay. So whenever process 0 is passing this message, process 0 generates this message. Along with this, there will be a list where in the list process 0's identification number will also appear. When it passes to process 1, the message, the modified version of the message will be like this. But in that additional list, along with process 0, process 1 will also be listed. Okay, so you have this modified message and a list containing all the processes through which the message has been passed. Okay. Now when this message, finally the modified message, the message part will be like this. In addition to this, there will be a list of all the processes 0, 1, 2, 3, 4, 6, 8 through which this message has passed. So when this message along with the list comes to process 0 identifies that there is a deadlock. Okay. Now it can take a decision that in that list, process 0, instead of committing suicide itself, it will request the highest numbered process to commit suicide. So in this particular list, instead of process 0 being killed, process 8 will be killed. Okay. What advantage do you get? Come to process 6. Process 6 generates this list, this message. Along with that, one such list will be generated. List in this case will also be same as list which has been generated for the message generated by process P0, because it is the same set of processes through which both the messages are being passed. Okay. So process P6 will get this message. Along with that, the list of processes. List of processes here will be 0, 1, 2, 3, 4, 6, 8. This is the list of processes which are attached to this message. Okay. It is the same list of processes 0, 1, 2, 3, 4, 6, and 8, which is also attached to this message. So you find that the lists are identical. Okay. So on receiving this message back, when this message comes back to process 0 will request process number 8 to commit suicide. That is the highest numbered process within that list. Here, process 6, when it gets this message, it will also get this list. It also finds that the highest numbered process is 8. So it will also request process 8 to commit suicide. Okay. So you find that only one process will be killed to break the deadlock, not more than one process. But the only problem is you have to pass more amount of information from one process to another process. But it has been found experimentally that in most of the cases, I mean almost 90% of the cases, the number of processes which are involved in deadlock is 2, not more than that. So the message or the information that is generated or which has to be passed from one machine to another machine is not much. So this overhead can be tolerated. Okay. So this is about the deadlock detection and recovery process. And obviously recovery means you have to kill one or more processes to break the deadlock. And obviously that is not a desirable situation because it leads to wastage of resources, wastage of time, because a process might have been executed for a quite long period of time, after which we decide that the process is to be killed. So all the computations that has been done so far becomes an wastage. Next time the process is initiated, this entire job has to be repeated once more. Okay. So the
how can we say that some of the processes are blocked? Every process is blocked.
Every process is blocked. Whenever a process is blocked, that generates the message. So here we have said that when process 0 is blocked, that has generated the message. After that, let us assume the situation that process 0 was not existing. When this was not part of the cycle, then process P1, process 1 would have made some request and it has been blocked by process 2. It is waiting for process 2 to release that resource. Process P1 will generate that message, same message. So the message in modified form will pass to all these processes and finally it will be terminated here. Or it will be terminated here. The same message, the modified message, will not come back to 1 until and unless this cycle is complete. Okay. So this process P1 will never identify deadlock. Whenever a process is blocked, that generates the message. But the message does not come back to itself until and unless the cycle is complete. It is not only this process. Whenever a process is blocked, the process generates the message. And the message passes from one process to another process in the chain. If the message comes back to the originator of the message, then there is a cycle. Okay, and how do you find that? You find out what is the originator identification number and what is the destination number. If these two are same, then there is a cycle. Okay, so every process generates the message whenever it is blocked. Clear?
In case of deadlock, each process is blocked in the cycle.
Each process is blocked.
So, sir,
So whenever a process is blocked, that has generated the message.
so sir, all the processes will be generating the message in deadlock.
But not simultaneously. If they are generated simultaneously, even then there is not a problem. That is a situation when at the same time instant, all these processes requests for some resource. All the process will generate the message. Every process will generate the message, and that is the worst case situation. Like in this case, we have said that if process 0 and 6, they are blocked simultaneously, they will generate the message simultaneously. The messages will go through this cycle, finally come back to these two processes. Process 6 will find that here the originator and the destination, they are same. Process 6 will kill itself, will commit suicide. Process 0 will find originator and the destination is same, it will also kill itself. That means both the processes 0 and 6 will be killed. If we don't make such a type of strategy. If all of them are blocked simultaneously, all the processes will generate the message. All the messages will circulate through this circle, finally come back to the process itself with originator number and the destination number identical. If I don't have any such provision, in that case, all the processes will find that all of them are responsible for occurrence of deadlock. All of them will commit suicide. But which will be avoided if we maintain such a list. Because the maximum numbered process will be unique. And every process, on finding out that there is a deadlock and the process is involved in the deadlock, the process will request another process having the highest identification number to be killed. Now the process, 0th process will not kill itself, or the 6th process, process P6 will not kill itself. But it will request process 8 because that is the maximum, that is having the maximum identification number. So both of them will request process 8 to commit suicide. They are not committing suicide themselves. If process 8 finds that it is also involved in the occurrence of deadlock, now the identification number of this process 8 is same as the maximum identification number. So the process 8 will kill itself.
So we have given that number, so how can we tell that?
You have not given that number. That number is generated by the system. Process identification number you never give.
Is the always highest number or is the request for resources is like this? Is there other way?
It may be highest or it may be lowest. I mean, some criteria has to be followed so that the victim process is unique. I do not want to have more than one victims. Because whenever there is a cycle, killing one of the process will break the cycle. So why do we want to kill more than one? Okay. So victim has to be unique. That is the aim. Okay. So this is the deadlock, distributed deadlock detection and recovery. So as we have discussed earlier, that to deal with the deadlocks, there are 3 approaches. One of them we have said that deadlock prevention, the other one is deadlock detection and recovery, and the other option is deadlock avoidance, for which we have already discussed about the Banker's algorithm, and we said that in case of distributed environment, we will not make use of Banker's algorithm or deadlock avoidance. In fact, even in centralized systems, deadlock avoidance like Banker's algorithm is rarely used, simply because of the problem that it is very difficult to know in advance what is the requirement of different processes. Okay. So though that is the ideal solution, but because of this difficulty, they are hardly used. So one of the methods, that is deadlock detection and recovery, that we have just discussed how it can be done in case of distributed system. Now let us see whether deadlock prevention can also be adopted for distributed system or not. Okay. So that is.
So you said that in 90% of cases there are only 2 processes involved in a deadlock.
Yeah, that is experimental data.
So is there any special protocol for saving the process on which more work has been done in such a case?
Yeah, in some cases, one criteria can be that we will kill the process which has been executed for minimum period of time, minimum duration. But the problem is, I don't know that what is the future duration the future time requirement of the process. It may so happen that I find that a job which takes total of 1 hour has been executed for 15 minutes. There is another job whose total time requirement maybe is a 13 minutes and that has been executed for 12 minutes. So only 1 minute is left. Whereas a job which has been executed for 15 minutes, for that 45 minutes is left. But if I take the criteria that a process which has been executed for minimum duration that will be killed, I'll kill process which has executed for 12 minutes, for which only 1 minute is left. Keeping the other process which has executed for 15 minutes, because I have assumed that that has been executed for more amount of time, so let me keep it to minimize resource wastage. Okay, so because you can never know exactly what will be the future time duration of different jobs, so whatever algorithm you adopt, everything will work best in a particular situation. There is no algorithm which will work best in every situation. Okay.
So in case of scheduling, we have assumed the completion execution time of the process.
That is predicted.
Can't we do some sort of predicting?
Okay, so let us see how deadlock prevention can also be adopted in distributed environment. So for deadlock prevention, we will use a method which is similar to the deadlock prevention method that we have used in case of centralized deadlock situation, but we tried to break the circular wait condition. And when we tried to break the circular wait condition, we have seen that we define a mapping function which maps the resource types to integer, and we have said that a process will be a request will be a valid request if a process puts a request for Rj holding request Ri only when f of Rj is greater than f of Ri. Okay, only that such a request will be a valid request. Otherwise, the process has to release the resources and then only it can put fresh request for another resource only when the condition is not satisfied. Okay. So following similar approach, we can try to deal with deadlock or try to have a deadlock prevention technique in case of distributed system. In our case, without using any such mapping function, what we will use is we assume that there is a global clock for all the machines in this distributed environment. That means whenever a process puts a request, every machine knows that when that request has been made. Okay. Also, every machine knows that what is the duration for which the process has been executed. Okay. Now, as we said that if we can break this circular wait condition, there will be no deadlock. To break the circular wait condition, what we will assume is, suppose we have a process P, okay, and which has been executed for say 20 time units. At this time, or say process Pi which has executed for 20 time units. At this time, the process puts a request for some resource where the resource is held by another process Pj. And suppose Pj has executed for 10 time units when this request has been made. Okay, identification of this is also possible because every process knows when the process has started and every process will know when the request has been made, and because of that global timing, it is possible to know that when the request has been made, what is the duration for which process Pi has executed, what is the duration for which the process Pj has executed. Okay, and our protocol will be something like this. When a process Pi puts a request for a resource which is currently held by process Pj, that means Pi is waiting for Pj. So now onwards, everything will put in the form of wait for graph instead of resource allocation graph. So whenever process Pi is requesting a resource which is currently held by process Pj, you just check that what is the time duration for which Pi has been executed and what is the time duration for which Pj has been executed. Okay. So if we find that the execution time already completed by process Pi, that is Ti, is greater than Tj, that is the already completed execution time of process Pj. If Ti is greater than Tj, then Pi will be asked to wait. Okay. If otherwise, if Ti is less than or equal to Tj, then Pi will be killed. A very simple strategy like this. Okay. So if I put this condition that if Ti is greater than Tj, then Pi will be asked to wait until and unless Pj completes and releases the resources. If Ti is less than or equal to Tj, then Pi will be killed. Okay. So if you follow this condition, you find that there can never be any circular wait condition. Because I can have a circular wait condition if the situation is like this. There is a process Pk, something like this. So if there is such a deadlock, such a circular wait condition, in that case, Tj will be greater than Tk. Okay. So I'll have the condition that Tj will be greater than Tk, Tk will be greater than Tr, Tr will be greater than Ts. Okay. And then finally, because Ps is also waiting for Pi, so Ts will be greater than Ti. Okay. So we started with Ti greater than Tj, Tj greater than Tk, Tk greater than Tr, Tr greater than Ts, finally Ts greater than Tr. So which by transitivity comes to Ti greater than Ti. A condition which is never possible. Okay. So this is never possible. So I cannot have such a kind of circular situation if I follow this restriction. Okay. So whenever Ti is greater than Tj, process Pi will be asked to wait until and unless Pj releases the resource, and then Pi will get the resource. If Ti is less than or equal to Tj, then Pi will be asked to kill. Again here our logic is because Pi, if Ti is less than Tj, that means Pi has been executed for smaller duration of time. Tj has been executed for a longer duration of time. Okay. So because Pi has executed for a shorter duration of time, even if I kill Ti, the loss will not be much. Okay. Of course, that is not true always. Right? So even this deadlock prevention algorithm we can extend to distributed deadlock situation. Okay. So with this we finish our deadlock topic.